The topic of this presentation is accelerated control and calibration, faster electric motor testing, and it's brought to you by HBK. There'll be a Q&A session, as always, after the presentation, so click the Q&A button on your screen to submit a question at any time. Also, the slides from the presentation will be available, and we'll post a link to download those in the chat box. So please welcome our presenter, Mitch Marks, Business Development Electrification, HBK. Welcome, Mitch.
Thanks, Chris, and thank you everybody for joining today. I hope you enjoy this session on accelerated control and calibration, faster electric motor testing. In the industry, we see a lot of people get bottlenecked in the development process by the control and calibration, just the sheer volume of testing it requires. Granted, we are a testing company, so it's near and dear to my heart. But we thought you'd be really interested in maybe some methodologies to accelerate that development process. So quick agenda. We're going to start with a little background. I never like to dive right into the weeds because you never know when there's a manager or somebody who might not exactly know all the background. So really hoping to help with the understanding of why these problems exist. We'll go through a little bit of the motor controller. You know, what the ins and outs are and what needs to be calibrated. Naturally testing. Then we'll look at some sources and delay and how to accelerate testing with a couple of examples. So with that, I will jump in. All right, background of powertrain calibration. So I think we're all familiar that the electric powertrain has a battery, an inverter, an electric machine, and a gearbox transmission, depending on the configuration. You know, we've got DC energy going into an inverter, and that AC energy going into an electric machine that creates torque and speed. But at the end of the day, all we really care about is creating torque and modulating speed. We want something to spin, and we want it to spin, you know, not too fast, not too slow. We want to get it there gracefully. So it's really about that graceful control of speed. And no matter what the product is, whether it's an aircraft, a power tool, a vehicle, we have the same configuration of battery, inverter, electric machine, transmission. And while these are all, you know, active or passive devices, there's a higher level computer that's controlling all this. And there's a higher level computer that's telling the inverter what to do based on the different states that these devices experience. And that's what we're referring to as the motor controller. But really, we're creating torque, modulating speed. Now, the fun thing about the motor controller, so kind of the motor controller being the conductor of this orchestra, it's got a lot of different states to account for. So in the battery, we have battery variables. We have the voltage level of the battery. We have the state of charge of the battery. We have the temperature of the battery, which I've evidently omitted here. In the inverter, we have some variables we need to consider. We have the type of control strategy we're using, so kind of the intricacies of what the inverter is doing, as well as the temperature. Again, always temperature dependent. In the electric machine, we have to account for the currents, the ID and IQ currents, the inductances, the DQ inductances, the flux state of the machine, and here especially, you know, temperature always very important to account for. Temperature is losses, so if we know our temperature, we know our losses typically. And then in the gearbox or the transmission, you know, we might again have to account for gear state. We might have to account for temperature. All of these have noise and vibration patterns that might need to be accounted for. So there's a lot going on, and I really state this to stress the complexity of this system and the higher level computer that needs to coordinate all of this. So the motor controller is managing transitions, so changes in speed, changes in torque, in the presence of many variables. So they're just, again, stressing that there's a lot going on here, and there's a lot of things we need to account for, because temperature is constantly changing how the system operates. Control strategy is changing how the system operates. Voltage level is changing how the system operates. And our controller needs to manage all of that. So this is what we're talking about today. All right, the motor controller itself. let's look at like the idealized motor controller, because I think that's the best place to start. So, and I reside in Detroit, so I'm going to reference back to automotive quite a bit. I imagine a lot of you are also automotive people. So we have a speed input. This is typically going to come from our pedal. You know, we push the pedal, we want to go faster. So let's say we're at a speed of 50 miles per hour. Or we're requesting a speed of 50 miles per hour, and our motor has an output, and our motor is outputting 60 miles per hour. So we have a speed sensor, we're measuring 60, and we're feeding that back. So we have this delta of 10 miles per hour. Cool. So what happens from here? Well, this delta 10 miles per hour goes into a speed controller that says, hey, I need to apply this much torque. And we get this torque kind of star. We get this estimated, I need to apply this much torque to get from 50 to 60 miles an hour. Okay, what do we do from here? Well, we need to compare to our existing torque. And in the ideal motor controller, our motor output has a direct torque measurement. We'll find out shortly that this isn't always the case. And we're going to take that measured torque, we're going to compare it, and we're going to get a delta torque. This is going to go into a torque controller, and this torque controller is going to use some math, use an estimation to say, okay, this is how I applied this much torque in my inverter. This torque signal goes to the inverter controls the motor. We have this nice closed loop feedback that's going to our load. So this motor controller, it's regulating torque and speed by measuring torque and speed and comparing it to the commands. This controller is going to take those commands and dictate the voltage and current of that inverter. And in that math, we're going to be accounting for external states. And my drawing would get infinitely complex if I tried to draw all those. But we're going to have some estimations. We're going to have some characterizations that tell us exactly how to get from 50 to 60 miles an hour. And we're accounting for those temperatures, those gear states, those voltages. So this is our ideal controller. The reality is a little messier. I think messier is the word I want to use. So in the ideal controller, we cannot measure torque. Anybody who's ever tried to measure torque in a vehicle realizes it's either very expensive or very inaccurate or not very reliable. Because vehicles experience a lot of rugged conditions, and ideally our torque is in the shaft of the machine, which we don't want to disrupt. So we can still measure position, or we can measure speed, this is our omega. But now we're getting angle, which is a cool thing, and that's pretty easy to measure. We use a resolver, encoder, pick your favorite device. But now for torque, we're going to be measuring currents, IA, IB. And fortunately for us, we can get a pretty good torque estimation from currents. We just have a lot of math behind it. So we're either going to measure 2 or 3 of the phase currents. We're going to measure that position and integrate to get speed. So we still have our input speed, we still have our measured speed, and we still have our delta omega. So this is cool, this is the same. This delta omega goes into a speed controller, we've got some current controls. This is just math saying, okay, this is what my system can physically do. This is the most graceful way to get from 50 to 60 miles an hour. And we get a current command that's going to be dictating torque. So now we're dictating current instead of torque. Okay, that's kind of neat. We're taking our currents, we're putting them through some mathematical conversions, and we're getting now to what is my flux or my ID, and what is my torque or my IQ. So we're saying we have these elements of current that represent torque or flux. Okay, we can feed these back. We're measuring current. We have a current command. And we compare these and we put them into a torque controller. And this torque controller, this is really accounting for all those state variables. It's saying, hey, I can go from state A to state B with this much torque, this gracefully. This is our characterization. We're then feeding those variables into a DQ conversion so we can get back to that inverter, and that inverter is powering that machine. So we can see in my purple, I've got math and estimation. We have a lot of math and estimation going on because we cannot directly measure torque, and because we still need to move gracefully from one speed to another. So there's a lot of math going on. We're estimating that torque and flux. We're not directly measuring it. We're estimating it from currents and voltages. We're estimating our command torque because we're taking that delta speed. So again, we're estimating how we get from point A to point B. And along the way, we're trying to maximize efficiency. We still need this vehicle to go far. So the output of this motor and the output of the inverter is only as good as the inputs, which are these currents and positions, and our mathematical characterization. And this raises the question, where does this motor, where does this inverter characterization comes from? It comes from a lot of testing to validate computer models, testing to validate states and how the machine operates in states. So this is where we start to get into, okay, we're doing a lot of testing. So I think this concludes the background, but I hope we're all on a good page with what we're doing. We're trying to allow the vehicle to estimate what its speed is and then change speed gracefully in any condition that a vehicle might experience. So what are some of the challenges for these in-vehicle controller measurements? Well, one of them, again, is all these different state variables we need to account for. Different torques, different currents, different voltages, different speeds, different temps. We also have to deal with the luxury of in-vehicle sensors. This guy on the right here, extremely accurate sensor, but it's big, it's bulky, it's expensive, and it's a little finicky. When I say expensive, I mean it's instrumentation grade pricing, not production level pricing. So your production sensors, well, they're cheap as chips. You know, you can put them into a vehicle, but their accuracy isn't great. They are, however, very reliable. So you're sacrificing accuracy for cost, reliability, and this is really allowing us to make a vehicle at a reasonable cost that consumers will buy. So, okay, we need to account for these in-vehicle sensors, which when your accuracy is a lot wider, you're guessing. You know, your guess is not as good when you have a lower accuracy. So you need to account for that. You need to understand that. We have all these operation states. And we have to worry about the reliability of our estimation for any given state. Did we account for every temperature? Did we account for every voltage level? Is something weird going to happen that we didn't expect? So the reliability of our estimations based on these production sensors, based on the number of states, is a real concern. And this is where calibration comes into play. We're going to account for all these states. We're going to understand the efficiency, the torque accuracy, the transitions in all of these states with our production sensors and in the lab. So what needs to be tested? I've said that there's this big demand for testing. What are we testing? First, I always like to start with what are we going to measure? Because I think before we really go to execute a test, we need to ask ourselves, all right, what are we measuring? So we're measuring efficiency. Again, we need this vehicle to go the range we expect it to. And we need to understand what is our most energy efficient point so that we can maximize that range and also minimize the environmental impact. So we're going to measure voltage. That's DC and AC voltage. We're going to measure DC and AC current. In a test stand, we're going to measure torque because now we're characterizing these machines. A lot of times we're going to measure vibration. You know, we do have to worry about the durability of these machines and also the noise and vibration concerns because vehicles have an experience element to them. A lot of times we're going to measure pressure and flow. This is to understand our cooling system and, you know, maybe how we're removing heat at different points throughout the operation. We're going to look at speed. Speed we always need to understand. That's really the important variable for us. And then we're going to measure temperature. We're going to measure a lot of temperatures, inverter temperatures, motor temperatures, battery temperatures, because this is a really important state. Everything changes with temperature. And then lastly, we're going to measure the communication bus in the vehicle. And I've called out CAN bus here. It's the most common, but there are several options. Because that vehicle controller, all the math it's doing, all the estimations it's making, it's going to publish onto a CAN bus. So if we're going to be reading this CAN bus and we're going to be measuring reality, we can compare what our controller is thinking to what's actually happening and check that accuracy of our measurements, check that accuracy of our estimations. All right, so what do we want to understand? That's what we're measuring. Well, we want to understand range. You know, we want to make that car go farther and farther. We want to operate more efficiently so we can maybe have less battery, have less weight. We want to look at transients. We want to make sure that we're getting from point A to point B quickly. When we press on the accelerator, we get that feedback we require. Or when we press on the accelerator, we're not breaking the gearbox with a big torque spike, or we're not giving a negative experience. We want to check our estimated torque accuracy, and not just torque, but current and voltage as well. We want to check the confirm that a very accurately measured torque value matches our controller estimated torque, or matches our controller estimated currents. So we want to confirm that what's happening on the CAN bus, this torque star or M star, matches a very accurate measurement. So that torque accuracy is a big part of testing. And then also we're going to look at failures. You know, how hard do we have to push this machine to make it blow up? And then we stay well away from that. And we have to ask ourselves, you know, what do the different control techniques I might be implementing do? What's going to happen if I go into a 6-step regime? What's going to happen if I inject certain types of currents? So these are the things we're trying to understand. And again, this is a lot of different tests. If we start thinking about it, okay, we've got a lot of measurements. You know, he listed 10, 15 different measurements. We've got a lot of tests. I think the picture is starting to get made. So we have all these measurements, we have all these tests, and now we also need to run these tests in a variety of conditions. If we're executing different battery voltages, so you know, if we're accounting for our different states of charge, the system's going to operate differently at each voltage level. So we need to account for that. We need to account for how much battery life we have left. That may also affect how we operate the system. We might want to operate much more conservatively for a lower battery than we would for a full battery. So we might need to characterize for the different operation state. We want to characterize for flux. You know, is the machine operating the same at every flux level I want? You know, do I have a good operation for every battery or a magnet string? And then lastly, or you know, if we're operating a hybrid, our system is going to operate differently in each gear state. So we want to account for that. And this could largely be efficiency. This could be torque ripple affecting how the gears mesh. This could be noise and vibration, or just system level efficiency. So gear state, but the top dog, in my opinion, the most important, I'm sure somebody will debate me and open to it, is the temperature. The inverter temperature is going to affect how the inverter operates, the inverter losses. The battery temperature is going to affect how much current it can discharge. The motor temperature is going to affect how the inductances are. It's going to affect you know, the magnet fields. It's going to affect demagnetization, but most of all, it's going to affect efficiency. So we have a big dependence on temperature. We really need to understand how this thing operates at a wide variety of temperatures. Can't stress that enough. To really maximize range, maximize effectiveness, and get those torque estimations right. All right. So what does a test stand setup look like? I think most of us here have probably seen a dynamometer. I'm not going to belabor this, but we have a load machine that is going to simulate test conditions. It's going to hold torque and speed, or it's going to run us through drive cycles. It's going to operate in these wide variety of different regimes. We're going to have a bunch of sensors. So our test stand is going to have a lot of sensors. And I have all these bubbles written. I apologize for this being a little messy. But we're going to have temperature measurements of the battery, of the inverter. We're going to measure voltages and currents of the DC battery. We're going to measure voltage and current of the inverter output. So we're going to be measuring those high frequency inverter signals. We're going to be measuring torque and speed of the electric motor. We're going to be measuring winding temperatures, and we're probably going to have a lot of measurements on winding temperature. And then in a lot of scenarios, we're going to look at vibration and noise as well, because experience is important. And here I have some HBM equipment, and I'll talk about that a little bit. I'll try to keep this not super commercial right now. But when we're looking at measurement or sensors, we need to ask ourselves, are we measuring all the relevant quantities? Can I actually perform this characterization? Can I make estimations on temperature state based on one temperature? So, can I guess my rotor temperature off of a single thermocouple buried in my windings? So we might need to make more measurements to complete these characterizations. Do our sensors have the accuracy to fit our needs? This is a thing I think a lot of people don't always think about, because you might say 0.1% accurate. Why would I ever need that? I'm 98% efficient. Well, if you're operating at 97% efficiency and you want to move to 97.1% efficiency, you don't even know if your change mattered with a 0.1% accurate system. So it's about the delta. So accounting for accuracy is, I can talk all day. This is not the talk for that. If you want to talk accuracy, please grab me after. But accuracy is really important for making changes. The same can be said for our measurement system. We need accuracy to fit our needs. We need to be able to trust these changes we're making. We need to be able to trust that our measurement in the lab is giving us a true value so that we can account for the inaccuracy of our production sensors. We need to trust that our measurement system has the sampling rate and bandwidth to really see our signals and trust them. And this actually falls into accuracy as well. But depending on what we want to understand, we need to have a good sampling rate. If we want to look at PWM signals and understand, how a control change is affecting torque, we need to be sampling at a high enough rate to see that transition happen. If we're trying to compare a vibration signal to an inverter signal, we need to sample at a pretty high rate. And then we need to make sure that these quantities are time aligned, because if we really want to understand, maybe how the device under test controller is thinking about it, we might want to measure its CAN bus. And we want that time aligned to maybe the measurements that a high accuracy system is making, so we can make sure we're comparing apples to apples, not apples to apples 30 seconds later. So time alignment is a really important thing. So went on a little bit of a measurement tangent there, but in the dynamometer test stand, we have a lot of measurements, and we do need to be concerned about accuracy. We do need to be concerned about time alignment, and having these things all in one place. Okay, let's get to the crux of it. In a little bit, but what are the sources of delay in a motor calibration? Well, delays in calibration, we have many measurements. We have data alignment. We have different data types. So if we have different systems, we might need to align data. We have different data types. Every department needs a test. So communication could be an issue. The NVH department, the control lab are all running different tests. So there's a lot of measurements. There's errors during tests. We might need to rerun tests. We might get some nonsense results. During our testing, the machine's going to heat up. The machine's also going to need to be cooled down, because we need to take all these measurements in a very tight thermal band, so we can really understand from the controller side how the machine is operating. We have a lot of measurement points. I've discussed all these measurements. We need to ask ourselves, how long does each measurement point take? Because there's potentially thousands of points. When we're doing test setup, we likely need to troubleshoot. Or if we're implementing a new control, a new design, we likely need to troubleshoot. If our measurement systems have black box equations, or we need to align a lot of different parts, this can make troubleshooting very difficult. So simplifying a test setup can very much accelerate setup, eliminate troubleshooting time. So lots of measurements, things can go wrong, things get hot and need to be cooled down, many measurement points, and just kind of the day-to-day life of reality. So these are some of our delays, and I think I'll dig into where this might come from a little bit. So when we're doing an efficiency test on a motor, we make some sort of engineering decision, and we have to ask ourselves, did this engineering decision work? Yes, the decision worked. No, the decision didn't work. We likely go to the next design. We need to evaluate this design. All right, have I run all my tests? Yes, no, I need a new test. Okay, have I finished all my efficiency maps? No, okay, move to the next test condition. All right, new test condition, new map. So we're running a new efficiency map. Has this map finished? No, move to the next torque speed point. Now I'm in the loop. Okay, set torque, set speed. So we're setting our torque and speed in the dyno. Are the conditions stable? Yes, no. So is our torque stable? Is our speed stable? Yes. Okay, now we need to ask ourselves, are we in the temperature range? No, we need to wait till we're stable. Okay, we're within the temperature range. Am I in the right band? Yes, take measurement. No, I'm not in the right band. So maybe I'm at 57 degrees when my test is, for 55 degrees. No, I need to cool down. And this takes time. This is an instant. So we're potentially waiting. All right, take the measurement. Is the measurement good? Yes, move to the next point. No, repeat this loop. So we can see that this can take quite a bit of time. And we might have to stop this on any point for safety, or because the dyno decided it was going to take a break, or because Johnny the intern wired something backwards, or because somebody opened a door and the test cell shut down. So these things can take a lot of time just by the nature of there's so many variables that need to be accounted for. We really need to fix these test conditions. All right, let's put some numbers behind this. So let's say an efficiency map is 200 points. I think that's a reasonable statement. And we want to account for 10 different temperature ranges. Our machine's going to operate in a wide variety of temperature states. This is a hybrid, so we have 5 different gears. And because of the battery, we have potentially 5 different states of charge or voltage levels we're worried about. Okay, how many measurement points is that? So we have 200 points, and we need to understand this for all 10 temperatures. We need to understand that for 5 different gear states. We need to understand that for 5 different states of charge. 200 times 10 times 5 times 5. That gives us about 50,000 measurement points. That's a lot of measurement points. And I've got a little graph here. Okay, what if I've got an older measurement system that might take 10 seconds per measurement point? 50K points, 10 seconds per point. We're looking at 139 hours. That's about a week. So that's a lot of time. Okay, 1 second measurement. We've 10x'd our time. All right, now we're looking at a couple of shifts. 13.9 hours, maybe that's 2 shifts. 0.1 second measurement, now we're looking at 1.39 hours. That's real fast. Okay, maybe because we're using a 10-second measurement, we go down to 20K points. Now we're only at 55 hours, but we can see that math continuing. And no matter how thick or how dense your map is, slow measurement eats up a lot of time. And this is before we consider that the dyno actually needs to make transitions. We can't just test, 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 test. We need to go from 50 Newton meters to 60 Newton meters. And there's mechanical settling time in that. Every time we're running a point, so every time we're taking a 10-second measurement, that machine is heating up, and then we need to take time to cool it down. So if we're testing faster, we spend less time heating up, less time cooling down. We're actually accelerating that test by accelerating it. This does not account at all for the other tests we might run, control tests, transient tests, looking at the torque accuracy. This also doesn't account for having to rerun tests. So when we look at time consumption, the pure number of measurements, the pure number of points really create this very complex setup that takes a significant amount of time to test and understand, because we want our vehicle to work. We want it to work the way we want it to. Okay, we're all experts in why these tests take a long time. What are some things we can do to accelerate testing? again, I'm going to try to speak generally, but HBM or HBK does make a significant amount of test equipment, and all the examples I'm going to give feature our equipment. So I think these are kind of intuitive things, but reducing the number of measurement devices, simplifying the setup will eliminate time alignment. It'll reduce data chaos. You'll have fewer data sources that you need to align. And it'll give you confidence that everything is going to, work in one common location. You don't have errors in setup. Decrease measurement time. We just went over this. If you can go from 10 seconds to 1 second, you're spending less time measuring, less time waiting for thermal. Recorded data. If something goes wrong in a test, you mix up, phase A and phase B, you put current sensor 3 in backwards, you don't need to rerun that test. You can take data and rerun it, with math. And less time you're on the test cell is less time you're spending money on running a test. It's less time you're not running a different test. So if you have data and you have the ability to identify issues, you can often rerun your test without needing to rerun tests. Real-time feedback, because this dyno is a physical element that needs to move states, if you can have a closed loop feedback from measurement to the test system, you can automate your testing and make it run faster, or just not have a person always there making sure everything's going correctly or physically changing points. We're gonna have faster transitions, again, accelerate that testing. And the one I think is probably most important is transparent and editable equations. If you know how all your math for power, for efficiency, for ID, IQ is being executed, you can simplify your troubleshooting, but you can also match the calculations in your test system to what's happening in your controller. And you can have confidence that the math in your test system is the same as the math in your controller. So you're not sitting there scratching your head over, a factor of √2/3, which none of us have ever sat there and wondered, is this √2? Is it √3? Is there a pi? You can have that real intuition. So these are some simplification methods. I'm now going to jump into some examples. Again, these were done using HBK equipment. So fast and accurate efficiency measurement is really a function of doing a dynamic power measurement. So let me take a step back. In our system, we use a thing called cycle detect, which is a digital algorithm that tracks the phase A current, identifies zero crossings of the phase A current. So in this diagram, I've got current in red and cycle detect in black. And we've got digital algorithms that in hardware are saying, here's a zero crossing, here's a zero crossing. We take that time period denoted by my square wave, and we say, okay, we're going to do our RMS calculations, our power calculations, our efficiency calculations on this time period. This gives us a near instantaneous power measurement that's also extremely accurate because of that cycle detect. This allows us to do things like measure power while transitions are happening. So if we look at my example on the bottom, this is a machine spinning up, starting from 0. And we have current in red, voltage in blue, power, apparent power, reactive power as scope traces in black, pink, and yellow. And we can see that this machine starts up, we get current, and our cycle detect is tracking that. We're then performing all those calculations so we can really start to view power, reactive power, apparent power as a scope trace. So we can start to understand efficiency during transients. One, this is going to allow us to do some flexible testing or understand the real drive cycles, what our energy consumption is during drive cycles, with a really high accuracy, mind you. But if we look at efficiency mapping, this is where I think the real power comes in. And this is a setup for my next slide. So accelerated efficiency mapping is something we get involved with regularly because of the cycle detect speed. With the cycle detect, in a couple of cycles, a couple of rotations of the machine, we can have a very accurate measurement. So we're actually looking at more of this 0.1 second or 1 second measurement period. So this is an example of an efficiency map. 293 set points. So we had 20 speeds, 17 torques, and they're all displayed on the right-hand side here. So each one of these little boxes is a speed, speed's in green, with a variable torque, torque's in pink, and then voltage and current in blue and red. If we zoom in on one of these, so this guy's zoomed here, we can see that each one of these little areas has 1, 2, 3, 4, 5, 6, well, I guess it's 17 different measurements. And we can see that, all right, we have a measurement. This measurement is 100 milliseconds. So we record for 100 milliseconds. We do all of those power, efficiency, torque, speed calculations. And then we have to wait half a second for the dyno to change speed. We have this really nice image. We have a whole test sitting in front of us. I mean, it's incredible. You're basically testing at the speed of your dyno. And in this 0.1 second, we're getting 10, 20, 30 cycles. So we're averaging an extremely accurate value very quickly, as fast as your dyno can go. And if we remember, we spend less time heating up, spend less time cooling down. Really great way to accelerate your efficiency mapping, because if you're running 250 tests at 293 points for all our different temperatures, gears, states of charge, that is a lot of time spent testing. And you can significantly speed that up with something like the cycle detect. So try to put my money where my mouth is. And then we also offer live efficiency mapping so that you can actually see that test being plotted in the real time as you go. And this allows you to have that real-time feedback, that validation, that engineering intuition as to whether this test is running correctly or not. Having live and custom equations is another powerful thing. So let's say you need to do a DQ0 transform or a space vector transform to really understand how your control is operating. So you might want to measure ID, IQ, and look at your torque on a screen. So you can understand that when you apply a load step, how your torque reacts, how your Q axis currents react, how your D axis currents react, and get insight on what's happening in your machine, and then compare this to the reality of what's being executed in the test, and compare this to what's happening in your controller. So if you're measuring ID and IQ and torque, and you're looking at your controller ID, IQ, and torque, you can really start to understand the accuracy of the system. You can compare this apples to apples, and you can get a ton of insight as to what's happening in the machine. Same could be said for a space vector control. Down here we have a space vector plot of alpha versus beta, and you can look at how your switching patterns are working. You can look at how your current patterns are working. So really powerful tool for, again, having that live engineering intuition. So these are being displayed on you as a scope trace. You're seeing ID, IQ as a scope trace, and you programmed ID, IQ so it matches the equations that you implemented in your controller. And here's an example of those equations being run. You can program in your resistance, your flux, and you can start to do your flux equations. And again, have that real-time intuition. Here's what my controller is doing. Here's what the scope of flux is doing, and see that in front of you. So a lot of power there when tuning these controllers and understanding errors between reality and the control. Having a CAN bus time-aligned, so reading that controller thought process, taking what that controller is calculating and reading it is really powerful. And this is a test we run very frequently, where in this example, I have real torque in pink, torque command, so that torque coming from the controller in black. And we can see that, okay, wasn't reading the controller, or the controller wasn't estimating torque. Controller kicks in, controller starts ramping up torque. But there's a delta here, and there's a big delta here. These are on the same scale. So this controller estimated torque and this real torque are fairly different values. Okay, I might need to tune this controller. And the only reason I have this data is because this controller was not operating correctly. Okay, let's look at current. Let's compare our current. So we have real current in red and that measured current in pink. or excuse me, that controller current in pink. Oh, well, okay. We have a giant delta here. Our measured current is much higher than our estimated current. I think our controller might have some math going on in it. This math might not be right. So we can go back. We can say controller current, no good. Controller torque, that might not be good either. But let's check. This gives us a really powerful tool to compare reality to controller. Again, we're going to accelerate that troubleshooting process. We're going to accelerate that understanding of what our machine is doing. And we're going to be able to fine tune it so that we can trust it. And we can trust those, not as accurate sensors. We can trust what our algorithms are doing. We can tune that system and make engineering decisions. So I think that's really exciting. Awesome thing to do. You could do the same thing with IDIQ. You could do the same thing with any variable you have in your controller, because you can execute custom equations in the real time. Rerunning a test. So with HPK system, we record all the data. We give you these equations. And a lot of times we get questions on the cycle detect and how good is the cycle detect? Well, I have an answer for you. Every system, every power analyzer on the planet is going to mess up cycle. Just fact of life. We fortunately record the data and also tell you the cycle time we use, so you can identify bad cycles or not, and then edit them in the data. So here I have some math for a bad cycle, and the bad cycle in this middle display is in black. And we get these big spikes or these big drops. And this tells me, oh, I have missed cycles, or I have I've doubled cycles, or I've missed cycles. And if we zoom in, we can see, okay, yep, I get these little spikes here, I get these little spikes here, or I get this big dead area. Yeah, these measurements probably weren't right, but at least I know. And then we can go back and we can tune some of these variables. So we can say, okay, my level was 0.1, now I want my level to be 0. So we're tuning that cycle detector. All right, my hysteresis 0.1. All right, now I want my hysteresis to be 0.005. And I want to change a hold off time. Okay, we edit these variables, and then we get this pink cycle detect where we can see, all right, problem solved, problem solved. So this is just an example. And let's say Johnny, the intern, wired current sensor 2 backwards. You can go in and do the same thing. Just go current sensor 2, -2. Beautiful, you're cooking. But this is a really great way to rerun a test without physically taking up dyno time, without taking the time to rerun a test. You can do it all in data. Or if you just forgot to calculate something, you could go back and re-execute that and get these cycle detects where you didn't have it. This is just an example of how data can allow you to rerun a test or run tests you forgot to. Lastly, feedback to an automation system. If we can close that loop on testing, we can accelerate our testing. And the HVM system allows feedback over EtherCAT, CAN bus, API, but we can also control our system through LabVIEW, C++, Python, TTL. And by having this closed loop, by giving data back to the automation system, so it can say, oh, cool, I've reached torque X, speed Y, voltage this, voltage that. I can run this test point confidently. And then I can say, system, move to the next point. And command, measurement, command, measurement, command, measurement. We can move through the tests more quickly, save time. So in conclusion, motor control and calibration is a demanding task. It's going to take up a lot of time. Measured data and measurements in general are important for the internal controller estimations. We need to have that data. Estimations are determined by extensive testing and measurement. And we have to take a lot of tests with a lot of points, with a lot of states. We've labored this for the last 45 minutes. And HPK can accelerate that HPK can accelerate that calibration process through some of the methods we described, like cycle detect, like recorded data, like transparent equations. So with that, I'd like to thank everybody for their time, and I'm looking forward to the questions we're about to get.
Great, thanks.